Hello and welcome. Again we will be discussing about functionals in R in this module. In this module we will start the discussion with the map and MATLAB function. We will show you what exactly, although both of them look same, but what exactly the difference between the two. We will give you some examples where actually functionals are not well suited. Instead of this, we should continue the use of loops in R. We will give you some of the hazards of using functionals in this module. So let's see what is there in this module. So here we are going to learn the use of map and MATLAB functions, the problems with functionals, and the use of PLYR package, and also where do we avoid using functionals. So before starting the discussion of what MATLAB and map function actually is and how it works, let's concentrate on the reasons why do we use the map and MATLAB function. In the previous module, we had a detailed discussion regarding the Laplace function. One of the problems with the Laplace function is that there, as we know, only one argument of the function varies and the others are fixed. But there might exist some cases where the problem demands to include more than one inputs. In those cases, the Laplace function fails to cater the need, and from that point of view, the idea of MATLAB or map function comes in. Let's take up an example to demonstrate it properly. Suppose you have two lists, both the first and the second, that is x and y, contain a set of 10 samples, each of size 5. Now suppose we want to find the correlation coefficient corresponding to each of the 10 samples. Then what do? How do we proceed? We can use loops here, but that has some problems as we had seen earlier. So think of how can we solve this problem using apply family of function. Since this problem involves two lists, so if you use the Laplace function here, then that would work in a clumsy way, like the one we have given here. Instead, try the map function. Just type the code that we have given here, that is map, then within the first bracket COR, the function which will find the correlation, and then the two lists for which we are trying to find the correlation, that is x and y. The output will be given as a list, and as you know, you can always unlist it using the unlist code command. So as we have seen just now, we can always convert a map function to a Laplace function which will iterate over the indices, but the map function will give you a more compact and less complicated code that Laplace function will give you. Now let's have a closer look at the arguments of the map function. Here, unlike the Laplace function, the function argument is the first argument and the list will be passed thereafter. Then the question that arises is, what is the MATLAB function? How it works? Is it the same with that of the map function? Let's take up these questions one by one. Both the MATLAB and the map functions are equivalent when simplify is equal to false holds. For the MATLAB function, simplify is set to true by default. It helps us to simplify the output as the supply function does. So as we know, this argument gives lesser amount of control over the output like supply function. As it had been shown here, for the map function, the anonymous function had been used to provide constant outputs.
but things are not exactly like that for a MATLAB function. Here it has the argument more args, which is more args, which takes a list of parameters to be kept as fixed during the iteration. So the syntax of the MATLAB function is like the one that had been given here. In the very beginning, as opposed to the Laplace function, the function should be provided. Then the list will be there as an argument, which has been shown in the dots here. Next, the arguments more args and simplify will come and do their respective jobs. And this is how the two functions MATLAB and map work. Now it is absolutely your decision in order to choose either of them. As we had seen in the previous case that we had more than one list on which we need to apply any function. Now the question is, what if the thing get reversed? That is, how will we proceed if we need to apply a set of functions on a particular list? We faced this problem before and solved it using list of functions. But the thing is, we can always write down our own function using Laplace or any function of this type and solve the problem elegantly. Here comes the idea of using some more complicated functionals. As we have discussed in the very beginning, functionals are something which are very useful and can be used effortlessly without making an error. Till now, our discussion was primarily based on how functional help us to avoid loops and to commit lesser amount of errors. Here, we will discuss about how functionals help us to execute matrix and other higher dimensional array operations. Why we are considering this? Because till now, the functionals that we used were based on one dimensional inputs. The question is, what if we use some higher dimensional data structures as inputs? How functionals will cater this job? Let's see how the whole thing works. At first, consider the apply function. Remember, most of the functions that we have considered and will be considering here were known to us. We must have come across these during any of the basic R courses, but the point of view from those where we were looking at these functions are the focus of interest of us. So the point of view are different in both the cases. So let's start with the apply function. Apply is a functional which takes matrices and arrays as input. Let's consider what are the arguments that it takes. Firstly, it takes the array to deal with, then you need to specify the dimension which will act here. If you specify 1, then the function will deal with the row as we know, and 2 will indicate the column. This is something which we had come across earlier. Then one needs to specify the function to be applied, and then the other functions should be queued. So let's demonstrate it with an example to have a more clear view. Consider the simple example. Let's construct a matrix with elements 1 to 6 having 3 rows and name it as MATLAB. Now let's observe how the apply function deals with the arguments. Here we are writing apply, then mat, comma 1 and sum as the arguments. So the objective is we need to deal with the rows of the mat matrix. That's why we have written 1 here. So if we use the function sum, then we are getting the row sums corresponding to the elements of the mat matrix. So as it's pretty obvious, if we substitute sum with prod function, that is product. That is, if we want to know the product of the elements corresponding to the rows of the math matrix, then we will get the outputs that have been shown here. Here sum is just replaced by product. So, this is how apply function works. But as we know, most of the things in the world comes with some hazards, and the apply function is not an exception to that. Remember, we have used the argument simplify somewhere before. The issue with this Laplace function is that it lacks this argument. Actually, it does not have the simplify argument. So, this indicates us you can never be completely sure what type of output you are going to get. This clearly shows that you should be very careful in order to use the apply function. Now, swept and outer are the two other functions which also acts as a matrix functional. So, these two functions will also cater our needs to handle matrix or higher dimensional arrays, specifically matrix. Next, have a look at the Tapley functional. Suppose we are dealing with a data set corresponding to 26 students. We can always simulate the data. So, let us simulate it. So, we are expecting the heights to come around 40. So, let us simulate a set of 26 data points from normal distribution with mean 40 and standard deviation 2.5. Additionally, what we are doing is that we are rounding these numbers off. So, we are storing these data points within the variable weight. Also, we are wanting to allocate the first 12 observations as the weights corresponding to the students of class 5, and the rest of the 14 will correspond to the students of class 6. So, just looking at the data, we can readily observe that the two groups will have different lengths. But when our data will be of substantially high length, then if we write down the Tapley function, then weight, group and length as the arguments, then we will be coming up with the lengths corresponding to each of the groups. So, the problems will be with higher amount of data, and here the solution is. If you replace mean in place of length, then again you will be having lengths corresponding to each of the groups. The same thing will hold for standard deviations as well. So, we are more or less familiar with the functionalities that Tapley function does, but let us try to find how it works. The thing that the Tapley function does is it works by creating a ragged data structure from a set of inputs and then applying a function to the individual elements of the that structure, particular structure. You can find the first task similar to that of the split function. What it does is it takes the 2 points and returns a list which groups elements together from the first vector according to elements from the second vector. The output which is given here will give you some ideas regarding the functionality of the split function. So, as you can understand, the Tapley function is just a combination of the split and supply function. So, before these sets of modules, we have used a number of basic functionals, maybe knowingly or unknowingly. We have discussed a few of them in these modules as well. We have used a number of apply family of functions in these modules as well. But have you ever come across any difficulty in order to use them? I am sure you did. Let me tell you some of the difficulties that users often come across. The function which are needed to be the problems that which are needed to be mentioned is that these functionals have been written and modified by multiple authors. So, it lacks consistency in some sense. There are some problems with the arguments of these kinds of functions as well. Like if you have a look at the first argument of most of the base functionals, then you will find a vector or the input that we are putting. The vector will be there. But can you remember what the first argument of the map function is? Actually, it is a function that you are wanting to apply on the input. Most of the problems are associated with the syntax only. Like for tapply, sapply and maply functionals, as you can see, the simplify argument is there, but you will not find this in case of the apply function. There is another thing which you might have looked at is that in tapply and sapply function, the simplify argument is written in lowercase, whereas in case of maply function, it is written in uppercase. So, uniformity is not there in this regard. So, you cannot memorize all these things. One more thing is that the maply function is a variant of the sapply function that allows you to describe what the output should be. But have you come across any of these variants in case the tapply, apply or maply functions? Surely not. So, these kinds of questions keep rising all the times. These kinds of problems restrict you to learn the functions systematically. Like suppose you want to use list, data frame and array for all the combinations of input and output. So, in all we will be having 6 combinations as it is shown here. It should be 9 combinations as it is shown here. So, as the table shows, I need to have 9 functions here, but based on the functionals that we have already learned, I am left with only 4 functions. So, what do we do? How do we proceed here? Here the PLYR package is with us for our help in this regard. This provides consistently named functions with consistently named arguments and covers all combinations of inputs and outputs of data structures. This can be shown through this table. Here, as you can see, the table is filled for all the 9 places having consistency in their names. Here, the 2 initial letters are based respectively on the types of inputs and outputs that they are taking. So, the table shows primarily the reasons why do we need to have the PLYR package and what are the things that it helps us to deal with. You can always use functionals in order to handle list. There are functions like map, reduce and filter. We have used this function previously, which always help you in this regard. We just discussed about these functions called map, and the discussions regarding the function filter and reduce, as we have told, we had discussed it previously. So, we know how these functions work. These will help you to alter and collapse a list. So, basically this deals with list, we all know that. Also, in order to perform subsetting, which we will discuss during the modules dedicated towards metaprogramming and non-standard evaluation, some things are there which are needed to look at. So, till now we have come across a lot of functionals that the basic R offers us. Now we will start discussing some of the very common functionals that you must have used previously, might be knowingly or unknowingly. Think of functions like integrate. What it does primarily? It helps you to find the area which lies under the curve given by some function. This is a simple built-in mathematical function for a definite integral. This will return a single value when the function is given. So, it works in a pretty simple way and we all know how it works. But you might be thinking why we are considering it to be a functional. What are the reasons behind that? Primarily, it does not look like a functional as we know. It looks like these functions are not used to eliminate loops which functionals usually do, which are the primary objective of applying a functional. Then why do we consider this? We will consider this because if you have a look at how this function works, then you must see that these work in such a way which would involve the repetition of the same kinds of things many times. So, these repetitions might not be visible at the time of working it, but it is still there. The functions like optimize and uniroot also work in similar ways. For the first case, we are required to give a function within an argument and try to find the point where the function reaches its maximum or minimum value. The second function, uniroot, works in such a way that we are required to give a function and then the uniroot function tries to find that point where the value of the function that was given an output attains the value 0. So, in both the cases, some successive iterations had been used to find the desired value so as to produce a single value as output. These can be shown through examples as well, but here we are not going into the details of all these things. So, we are at the last part of our discussion. In the last 3 modules, we came to know what functional actually is, what are the different kinds of functionals that R offers us and many more. So, primarily it helps us to replace loops and makes the program shorter, also easy to understand and less error prone at the same time. But here the question that must be roaming around your mind is it true always? By this, what I mean is, can we always find a functional corresponding to each looping structure? Also, even if we find one, does it worth replacing them with functional? I mean, is it beneficial always? Of course not. There are a number of cases which shows that it is not worth replacing all the for loops. Let us consider one of them. In real life problem, we often come across situations that requires to handle recursive relationships. Like in the case of exponential smoothing, in order to compute the values, we need to take a weighted average of the current values as well as the values which came previously. In this case, we can't eliminate the for loop for the sake of just eliminating it as we have done before. So, we cannot eliminate the for loop and replace it by functional here. That should make sense always. You may come across these kinds of problems for while loops as well. As we already know that the while loop is a generalization of the for loop, some kinds of conditional statements are there. So, we can always convert a for loop to any while loop, but the converse is not always true. This is very obvious. Some of the times it is possible to replace a while loop with a function. There might be a handful of cases considering this, but again things are not like this always. Sometimes you might find it difficult to get a function replacing this.
So, as we can see from the discussion of this module, we can have the idea of how the map and MATLAB function have been conceptualized from the shortcomings of the Laplace function. In this module, we have discussed about the shortcomings of the functionals as well, where it is not wise to replace loops with functionals, which we usually do in order to execute some computation in statistics. So, with this note, we are concluding the discussion of functionals here. Indeed, some more things are needed to be discussed in this topic, but we are stopping here and we are concentrating on some other topic from the next module onwards.